Hey guys, this is 12.5 through 12.9, and when we talk about 12.5 and 12.9, through 12.9, we're going to start talking about, there's three big concepts that we want to talk about. The first one is interference of sound waves and what we essentially call beat frequency. Okay, the idea is that when you have two sources that are playing a sound, depending on, even if, so it's the same sound, let's assume that they're the same. Depending on the distance you are away from the source, okay, based on angles and all that kind of stuff, there will be spots where the two sources, the two sounds, work together in harmony to make an even louder or stronger sound, and there will be times when they interact destructively, and they will interfere with each other and cause destructive interference, which means we're going to end up with essentially a dead spot. Okay, and so what that means for us is that depending on the design of a room, depending on the qualities of that, and the qualities of the speakers that we're producing and what sounds we're making, we can create places where it's difficult to hear. Now, that sounds like a bad thing, but what we also want to realize is that if we have active noise cancellation in like headphones, that's actually what we're trying to do. We want to take the outside world and interact with it in a way that we get very little of that sound through. That we create inside of our own ears a dead spot to the outside environment. Now, we still want to be able to hear our music. So this is a very complicated process that it's actually pretty cool that it's even doable at all. The idea of gathering information and trying to produce noise in order to cancel out the white noise around us. It's a very cool thing. Anyway, you can see a couple of models here where we're talking about A and B coming together at point C right here, okay, in a constructive way, right? So we can see that they're meeting together at a crest. And then we can see an example right here on point D where they're meeting together destructively, where one's at the top of a crest and one's at the bottom of a trough. And they're going to cancel each other out. And that's going to lead to less noise there. Okay. But what's actually kind of cool about it is that if we play two sounds that are fairly close together in frequency, that we start to get every now and then points when the two sounds cancel out and we get no noise, and every now and then when we get them to hit peaks together and we hear a lot of noise. And so if we kind of go through that process, we hear something different than just each note on its own. We will hear what's called a beat frequency. You can often think of it as a wah, 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 wah in the background of a sound. You'll hear the sound, but then you'll hear sort of an oscillation in its volume. That's called the beat frequency. And the beat frequency is the difference between the two frequencies that we're hearing. So if I have one of them, for instance, that's at 50 hertz and one that's at 60 hertz, the beat frequency that I would hear would be 10 hertz, okay, 10 times a second. And so that is something that's really easy to make a calculation on, but it's also a way in which we can do things like tune instruments. If you think about it, when two notes are not quite in tune with each other, you'll hear that wobble. And as you narrow them together, if you lock them in just right, you won't hear that vibration anymore. You'll hear a constant sound. The second thing that we're going to talk about, this is a big deal, is the Doppler effect. Now, the Doppler effect has everything to do with the relative motion between a source of a sound and an observer. It also works the same with light. But this concept that if you take a fire truck and it plays a frequency, its siren, without moving, we will all hear the same pitch or same frequency in that. Is it a high pitch? Is it a low pitch? The same frequency no matter where we're standing. It'll get louder as we get closer, but the sound pitch or frequency doesn't change. Now, that being said, if the fire truck is moving towards us, right, as it moves towards us, those waves, as they're released, pile up on top of each other, and we end up with a much higher observed frequency in the front. Back behind, as the wave is released and then the truck moves before it releases another wave, they start to spread out. And that spreading is going to create a lower frequency that's observed by a listener. Now this can be done either by moving the source or by moving the observer. The reality is that as we have relative motion to one another, we're going to get a frequency shift. Okay, and this is called the Doppler effect. The formula for the Doppler effect is a bit of a doozy, but there's a cleaned up version that I really like to use right here. Okay, this is the Doppler effect equation that we're going to use in class. It says f prime, which is the new frequency, is equal to the original frequency that's produced by the source times the velocity of sound. Now, most of the time we're talking about the velocity of sound in air, which would be 343. But this still works underwater, it still works in space. It's still, I mean, although sound doesn't travel in space, but light does, and so we'd have a shift there. So there's velocity of sound on top and bottom. On top we have plus or minus the velocity of the observer. Is the person who's listening moving relative to the other? Are they moving forward towards it or away from it? Those are important questions. And then on the bottom it's minus or plus the velocity of the source. So maybe I'm standing still as a listener, but the fire truck is coming towards me or driving away from me. I'm still going to see the Doppler effect take in and make an impact. Couple of things. If you expect the frequency to rise, okay, use the upper sign. So if you think about it, when two things are getting closer together, you hear that, and the frequency goes up. As that's happening, we're expecting the frequency to rise. So as gaps close, frequency goes up. We would use the top sign in both of these situations. Positive here, negative down here. If we expect the frequency to go down, use the lower sign. Meaning, you hear the coming up, you hear that drop out in the frequency. It's telling you that you're going away from the source. Maybe the fire truck has passed you. If the fire hydrant moves past you, be very concerned. Okay, anyway, sorry. If the fire truck has gone past, you're going to hear a dropping in the frequency. That's something that hopefully you're comfortable with using and being able to manipulate. The last thing I want to talk about is sonic boom and shock waves. And the basic idea is that if we get going fast enough that the object is traveling very close to or faster than the speed of sound, these pressure waves get stacked up on top of each other. And eventually all of that energy that's stored in that pressure wave will release and you'll get a shock wave. Very, very cool thing to see in real life. And you can hear it. Now there are usually two waves, but they're usually so fast together we can't tell the difference, but there'll be the front and the back of the shock wave. And that shock wave can actually cause distortions in light. And you can see that in this image. If you look at it closely, you can see that it bends light because the pressure in the air has actually created a bend in it's like a rainbow. You bend the light that passes through. There's two formulas we're going to talk about. First, if you want to know the angle, okay, of the cone that comes out from the sonic boom, you take the sine of theta will equal V of the sound divided by V of an object. Now, remember, sound doesn't always travel the same speed. As you go up in elevation, the velocity of sound will change as the air density changes. So depending on where you are, the sonic boom can occur at different velocities. And then it's divided by the velocity of the object. If the object is not going faster than sound, then this number right here, and remember your trig just a little bit, if the sound is bigger than the velocity of the object, this would be would be greater than 1. Well, the sign is never greater than 1. It's bounded between -1 and 1, never bigger. And so we can't get a sonic boom if we're not going faster. Okay, I can't get that shock wave if we're not going faster than that. The other thing that we're going to talk about, it's a small thing. Most people kind of get a sense of it just if you hear enough pop culture references. But when we talk about a Mach number, not like Gillette's Mach 3 turbo razor, you used to shave, but we're talking about a Mach number that has to do with speed. It's really just the velocity of an object divided by the velocity of sound. Are you going 1.5 times the speed of sound? That'd be a 1.5 Mach number. Are you going twice the speed of sound? That'd be a 2.0 Mach, or we call it Mach 2.0. So that is just a way to reference your speed relative to the speed of sound. All right, hopefully that's a lot of good content, and hopefully it'll help you get through the homework questions. I'll see you guys in class.